So this is based on basically two papers. So this is the paper I sent. The other paper is in progress. That's the reason basically it was supposed to be a single paper, but it didn't work out. It was a big project with my longtime co-author Tayfun Sönmez and my new co-author Haluk Ergin. What did we do? So if we go back a little bit, this kidney exchange process, the mechanism has become a widespread modality of transplantation throughout the world, most of the world. So in the United States alone, through this exchange process, about 500 patients receive a kidney transplant every year. That's about 10% of live donor transplants. I think it's still low. There are some other reasons why it's low, which I'm not going to talk about today. But if you think about it, why we have this exchange, the exchange is there mostly because there's live donation possibility. And there's live donation possibility, so therefore, there are some medical incompatibilities or other kinds of incompatibilities. So we can create these exchanges between live donors to create mutual compatibilities. So this could be applicable to any kind of organ for which there is live donation chance. So if you think like this, then this becomes more like an organ exchange. And then the question is, well, what is different from kidney exchange? The first thing is, it turns out there are many differences, both theoretical and implementation level, for the organs that I'm going to talk about. And why donation? I guess it goes back to this ethical question, can we sell or buy human organs? And the current realm of this debate, which is an ongoing debate in the world, is that human organs cannot be received or given in exchange for what's called valuable consideration. And this is explicitly written in National Organ Transplant Act of 1984, and World Health Organization has also condemned this practice over the years. But there was an amendment, so what is a valuable consideration? That was up for debate, especially in the US. So, okay, if you get a car for a kidney, it is valuable consideration. But if you get a kidney for a kidney, is it a valuable consideration? It was clear it was not, but it had to be amended in 2007. And now, then actually, this live donor kidney exchanges have taken off. I mean, kidneys are by far the most transplanted organs. So, but they are followed by, for the live donation, livers and lungs. And especially in the recent years, live donor liver and lung transplantation have increased in the world. So I will talk about these two organs, basically. I will give more details about this. So livers, so it's kind of different, right? In the kidney, we have two kidneys, so you can give one of the kidneys and the donor can live a very good life usually with one kidney. Not many complications occur. But if you think about the liver, we have only one liver. But it turns out that liver is a very resilient organ, and you can just cut it off and then it regrows in the person. Of course, you have to do it in a particular way. And usually what happens is that one donor donates the smaller usually part of the liver. It's not symmetric. That's the left lobe. And then both pieces in the patient and in the donor regenerate, and they become full liver. Lung is a bit different, actually quite a bit different, because for lung transplantation, actually you need two donors, not just one, for a single patient. And what happens is that basically, you have to come up with two compatible donors, and each of them is going to give a lobe of their lung. So lung doesn't regenerate. So if you wish, we have two lungs. I'm going to show you a picture, and there are four, all practical purposes, there are four lobes. And a donor can only donate one of those lobes. So you can, they basically cut half of one of the lungs. They cannot do the other one because then the person becomes disabled. So they don't want to make a donor disabled. Therefore, you need a second donor who would give 1/4 of the lung volume. and then these get bigger, although they don't regenerate tissue. They get bigger to fill the cavity, and they start to work. It looks very difficult to coordinate, but it has been done successfully, especially in East Asia, that I'm going to talk about. And among these, liver exchange has already started being conducted in Korea. And you would think that it's very similar to kidneys. So why because you still think one donor, it's almost the same principle. It turns out there are some important differences that I will talk about in a minute. But lungs is clearly, even you can tell from looking at it, that it's a two good exchange problem instead of one. And it will have some other peculiar features because of that. So the contribution of these two papers is going to be basically, this will be the first paper in the medical literature or anywhere that we know of, which will propose this live donor. It's called lobar lung exchange because you give just one lobe. So this is the first paper which proposes this. And we model this liver and lung exchange as matching problems. We look at how, what can we learn as if you, so it's like we solve some sort of an operations research problem in the most of the first paper. We look at what are the characteristics of maximal matchings, how can you implement them. So there are not many incentive issues with the lung exchange. So we mostly look at under different institutional constraints, what are the most easily you can do this, and what are the gains out of that. And we propose some simple algorithms, but you can always use more fancy integer programming to find, although it's not going to be efficient, you can solve that. But to get some insights about how the efficient exchanges look, we develop some algorithms. But the liver exchange, from an economic point of view, is more interesting because it has more, it has a following paradigm. So unlike the kidney exchange, we have another constraint in this case. It's called size compatibility. It turns out that you need a large lobe so that you can survive. So although the lobe generates initially, you have to survive that transplant, and the liver has to start functioning before it grows. So that initial period is very important. So we have this size compatibility requirement. So you can only usually receive a left lobe from a person who is as large as you are in terms of BMI or weight or height. They have different standards in medicine, but usually you can say that you can only receive a left lobe from a large person as large as you are. But if you look at that, the population is such that mostly males get this disease, the end-stage liver disease. And many people who donate are their significant others, who are usually females. And when they come forward, usually the female is smaller in size than the male. So that becomes a huge problem. So many women actually donate their right lobe because of this. Right lobe is the bigger size, so it's much riskier for the donor to donate. If it's successful, great, but the right lobe is bigger, it's much riskier for the donor. So the question is, we address is, not only we look at the maximal size exchanges, etc., how it works, but what does this size compatibility requirement bring or take away? Okay? I mean, clearly, if you don't have the size compatibility requirement, which means that it will be riskier for the donors, okay? But there will be more donations, clearly, but only in the absence of exchange. When you put exchange, by putting an extra difficulty in direct donation, which is the size compatibility, actually you can increase the overall number of transplants. So it will be safer for the donor, and it will be increased. It will you can actually potentially have more transplants if you didn't have exchange, with the addition of this more difficulty in transplantation. Actually, this is just one example of these kind of things happen. So we have another project going on. Actually, it turns out that many things you would think, especially in transplantation, many medical doctors come up with these great ideas, right? So let's get rid of incompatibility Okay, so they come up with drugs, they work on these important drugs, and then they get rid of incompatibility, so the exchange is, they say, redundant in a way, because now the person who would like to donate can directly donate to the person his patient or her patient. Maybe kidneys, this is pretty good, but for livers, well, you cannot overcome size incompatibility. Size incompatibility is there, but you can maybe get rid of A blood type, B blood type, which I will talk about, blood type incompatibility to some degree, although it decreases the quality of the, but then, I mean, clearly this can create some problems, because now maybe you are decreasing some people who would like to, who would otherwise go for exchange and save another person. You make that person directly receive a liver transplant from his significant other, so only one couple or one patient is benefiting instead of two people exchanging. Because it's usually notoriously difficult to make somebody go for exchange when you have a compatible person. Just it's very difficult to persuade, etc. So we look into that. Under what conditions this liver exchange is going to be good? I mean, size incompatibility requirement is good, actually, this additional level of incompatibility. So this paper is still in progress. There is another an incentive problem there. I won't be able to talk too much about that, but I will give you some issues. But I mean, there are some people still they would like to donate their right lobe, which is the larger lobe, which is the riskier lobe. Even though they know all the difficulties, dangers to themselves. So can we come up with a mechanism which would basically, these people would, if we can, we are going to make use their left lobe, which is the smaller lobe, which is the less riskier part of the donation for the donor. So for exchange, these people will go for left lobe, but if we cannot find anybody to match them, in the end, they donate their right piece to their own loved one. Okay? So in a way, can we incentivize? So we don't want people just lie about it and come forward. Okay, I want to just donate my right lobe. We want to only screen the people who are really willing to donate their right lobe. So that's the incentive problem. We have some ideas, but I probably won't have time when I talk about all of them. That will be another talk when I finish that paper. So we simulate the gains from exchange, both lung and liver, so they have different contributions. So I guess lung exchange has the following feature. You already realize you need two donors, okay? So in kidney exchange, as you saw from empirical evidence, the increase was about 10% increase in the live donation, okay? Even if you push it to the limits without using compatible patient donors, you will only have about 30% or let's say 50% of the gain at most, okay? But in lung exchange, direct donation is actually very difficult because you need two compatible donors. So through simulations, we show that actually a lung exchange is probably the way to go because it can almost triple the number of transplants. Not just increase the live donation by 50%, not increase it 1.5 times, it can increase by 3 times, including lung exchange. So that's, I think, in a way, application-wise, I think this is the most important contribution. So I will talk about this implementation later on if I have time, and in the end, how this can work out. So there are many papers on kidney exchange. I was lucky to be part of this literature, and there are other people who have worked on it. So this is a very now vastly incomplete list. There are some job market candidates this year in the market who are working on dynamics of, for example, exchange or other problems in kidney exchange. So, but there is a huge literature. For liver exchange, we are aware of only 3 papers. So 2 of these papers basically document the liver exchange programs in Korea and then in Hong Kong. So those are the medical papers. And last year, Thomas Sandom, who has also worked on kidney exchange, and his co-author Dickerson, they have a paper. They look at liver exchange program being run together with kidney exchange, and you can exchange a kidney for a liver, for example, that kind of cross-organ exchanges. So they show that in a large population, the gains will be significant if you have liver exchange being operated. So it will be linearly more people you will be able to save with the population size. And lung exchange, like I said, I think this is the first paper we know of. Okay, so to give you the idea, how am I doing in time, by the way?
Well, plenty of time.
Well, that's a dangerous...
47.
Okay, great. Okay, so I can give you just a bit more background about this live donation in this case. So live donor liver donation is most common in the Asian countries. And there's a reason for that. So this is different countries, each of them. The first line refers to 2006, and the second line refers to 2010. And the numbers above the zero axis are deceased donor transplants. The numbers below the axis are live donor transplants. So countries like Spain are very, very successful in deceased donor donation. So they have very little live donation programs. But if you come to the Asian countries, for cultural reasons, for legality of definition of somebody being dead donor, because you need like brain dead, and some of these countries don't recognize brain dead, these numbers are much less for these countries. Although there's an increase in 2010, for example, in Korea for liver donation. In Japan, there is none, zero. Okay, which is very interesting. So these countries have gone to the alternative route, and they've started to utilize live donation quite a bit. So our envisioning is that these exchange programs will not going to work in the West because they can utilize deceased donation quite a bit. There is very little volume of live donation. Maybe in the future, if once you prove that it's going to be successful here, they will also adopt. So this is the liver. So the idea is that you want to look at left and right. So just forget about there are 8 sections. So left is smaller, right is bigger. So they cut it basically from here. Either they give this part or this part. The other part stays. So this is the left lobar donation. This is the right lobar donation. Left lobe is about 40% of the liver. And the donor mortality rate is about 0.1%, 1 in 1,000. While this is about 5 in 1,000. So clearly this is much more risky, right, donor mortality. And there are other complications which follow the donor. This is just the mortality rate. So clearly this is the safest option. This is much risky. And what do you need for live donation? So I'm going to leave this here because I will talk about this quite a bit. So you need blood type compatibility. So O blood type can donate to A blood type, B blood type, and AB blood type, all blood types, while A can donate to itself or AB, B can donate to itself or AB, and AB is just the receiver. It can only receive or donate to itself. Okay? And that's caused by the lack of or thereof antigens. So you will see in the talk, I'm going to denote O as a 1 type. So this means no A antigen, no B antigen. So if there's a B antigen, you get 0. So I can denote this as a binary, 2-dimensional binary vector each type. So this will going to be 0, 1. This will be 1, 0, and AB has both antigens, so it's going to be 0, 0. So now I can create greater than or equal to relationship to denote who can donate to whom in this vector. So that's how I'm going to model. Yes?
What proportion of the population?
So this is going to be about 45% in the US. It's a bit less in other countries. A is about 40%. It can change between 30 and 40. This is about 11%, and this is going to be very little. And sometimes I'm going to just ignore this. It's solid or 4%. Okay, for some reasons, technical reasons. I'm not going to talk too much about AB. The second thing you require is, besides this compatibility, you need, actually, you don't need, there is another kind of compatibility. So unlike these kidneys, you don't need that because liver is very resilient. So it turns out the antibodies in your body cannot reject it. Even though they want to reject it, just liver survives. So this is not going to be a problem, unlike in these kidneys. But now we will have this problem, size compatibility, okay, which is not a big problem for kidneys. But now this is going to be an important problem. So a patient requires a graft relatively large to survive. So in terms of my model, I will assume there are only two sizes. So because I want to keep this kind of binary structure, but I can make it a bit continuum, but the algorithms change. So I don't know the answer yet, those. So what I'm going to do is that there will be a cube. You'll be large, so that will be the third dimension, or you'll be small. So this partial order, greater than or equal to, will determine whether you can receive from a donor of that type or not. So I will come to that. But that will be the additional dimension, this third dimension. And that cubes, if you make that side continuous, you would have different sizes, and you can only receive somebody as large as your own. So you can make it that kind of partial order. But I will, for the paper as well, we will just talk about this binary types. It will be small and large. One thing about this right lobar before the formal other models, right lobar transplant. So if you want to look at that, this black area, so this is until 2002 in Japan, is the right lobar transplant of liver. The others were all like different kinds of left lobar. So left lobe can be also divided to different pieces. So this number has increased. So people began to use this more risky side, and there's a reason, because they need more, and size compatibility is a problem. And this kind of live donation was invented in the US, but there was a very high profile death in the US where the donor donated his right lobe, and then basically this caused, because of the negative publicity, most of the live donation operations just didn't continue for a long time. So there were investigations, etc. And this not only affected livers. Actually, if you look at the data, Gary Becker had a paper at some point. He was looking at, there was a dip in the live donation for kidneys because it affected as well kidneys as well, because it creates a huge negative publicity. So it's important. We would like to, clearly just for personal reasons, we would like not to kill the donor, but it's also about the survival of the program in the long run. We would like to have a better way of dealing with. So liver exchange was first done in Korea, followed by Hong Kong, and there was one in Turkey. So I cannot write Turkey's name to this kind of medical invention, so it's nice to have it there. Liver exchange can have two benefits. Okay, like I said, it can increase the number of transplants, even though you add the size compatibility constraint, which I'm going to talk when you don't have the size compatibility constraint, according to that. Okay, and it can decrease this right lobar transplants, so you can give safer transplants to the people. So that will be the major tell of that. But now I want to talk about lung donation and lung transplant. So what I will do is I give you a toy model of liver transplant. I'm going to talk more detail about lung transplant. Then I will come back to liver transplant. So in the lung donation works as follows. Like I said, you will need two donors. And one, these are your lungs, and one donor gives one lower lobe, and the other one gives the other lower lobe, and the recipient basically gets these two lobes. Again, you will have size compatibility requirement, so you cannot, if the donor is too little, you cannot receive from him or her. but these pieces get larger and they they fill the cavity, so they start to work. Okay, so like liver, you need size compatibility and blood type compatibility. But again, this tissue type compatibility about tissue rejection, there's not much consensus yet, and usually, especially in Japan, they do it because Japan is a big leader in lung transplantation. They don't really check for tissue type compatibility, but there's not enough data to say that in the long run, maybe this will cause more rejections, etc. So there's no data to check that this affects the long-term survival rate of these organs yet. But we know from kidneys that this could be an immediate rejection problem, and on top of that, in the long run, this could affect the longevity of kidneys. Yes.
What's the survival rate now of this?
How many years? Yeah. It's actually quite long. It's more than 5 years definitely, but I don't know the exact number. I think it's more than 5 years. It is close to 10 years, let me put it that way, for lung, which is actually a huge amount of time. Half-life. Half-life is close to 10 years. Yes. But it is not as long as kidneys, which is more than 10 years, basically, half-life is, yeah. Okay, so clearly finding two compatible donors is difficult, so lung exchange can substantially increase the number of transplants. That's the idea. But, oops. Oh, it happened. Okay. So unlike kidney exchange, the combinatorial possibilities of matching is quite rich. So in the kidney exchange, we had one donor. So I'm going to compare it with kidney exchange. So there was one kind of basically two-way exchange, which matches two pairs. So each patient is denoted by himself and two donors. In this case here, each patient is denoted by himself and one donor, let's say. So there's only one kind of two-way exchange. But for the lung exchange, there are two types of two-way exchange. You can either trade two donors or just one donor, depending on how you get matched. And three-way gets even more interesting. There are 5 different three-way exchanges. 3 of them are symmetric, 2 of them are not symmetric, in which you either trade both donors one way, or you trade in opposite ways, or you only trade one donor, and the others are, these two are asymmetric kind of exchanges where this is like a central node. This is a bit, again, this is not, yeah, it doesn't have a very nice like network explanation, this one, but you can see how it works. And then 4-way, I don't know, so there's a, clearly open graph theoretical or Ramsey model kind of question. What happens? I'm not sure how it is that much interesting if you go beyond 4-way, 5-way, 6-way. But mathematically, as far as I know, this is not there's no answer to this kind of a question. And what we do is we are going to introduce an umbrella model for organ exchange. So there will be, so here is how it works, okay? Each patient in need of an organ has K attached donors. So I can make this K greater than or equal to the number of requirements. So, but for the talk, I'm going to make it exactly equal to K should be equal to exact the number of required donors, okay? So if both of them are compatible with her, she receives from them, okay? If both, meaning that here for lung exchange, of course, because I didn't say K equals 2, but whatever that K number is, if they are all compatible with her, she's going to receive from them. Otherwise, she's going to participate in exchange, okay? So for now, the preference, I will assume just is compatibility based. Either you are compatible or not, that's it. And the compatibility is determined by blood type, tissue type, potentially, and the size constraints, okay? So blood type is important for all these 3 organs. Tissue type is only important for kidneys. It could be important for lungs, but nobody really checks it, so we don't know, okay? But size is important for lungs and livers, while it's not important, that important for kidneys. So roughly the idea will be each patient can get grafts from donors that are at least as heavy or tall as herself. Okay, but roughly that's the idea. So these are the requirements. Number of required donors is going to be k equals 1 for kidneys and livers, and k equals 2 for lungs. And this model 0 is the kidney model that we talked about before in our paper with Al Roth. There we looked at exactly this model, and we looked at what are the best ways of conducting exchanges in an incentive compatible way. What does incentive compatible mean? Like, you are not going to be discouraged by bringing, you are not going to be discouraged from bringing more incompatible donors to the system. We are not going to penalize you when you get more possible transplant issues. So we call it donor monotonic. It was efficient. It has very nice, it had a matroid structure. It has very nice problem, and it was studied, how to solve the maximal exchanges was studied in the operations research literature years ago, called cardinality matching problem. So we used their algorithms to adopt these mechanisms, these rules we came up with. But now, for a lung exchange, we have a different model. We have two donor requirements. Size incompatibility, to start with, is not needed. So I will assume size compatibility is not needed. Tissue type incompatibility doesn't exist. Only we will check for blood type compatibility, which is over there. Okay. But now there's an equivalent interpretation of this model. The question was, which blood types are the most common? By far, in most of the countries, A and O are about 85% in the US, and it doesn't usually go 75% below. Of the population is made up of A or O blood type patients. Okay, and in this interpretation, this equivalent interpretation, so let's get rid of this B antigen. So let's forget about B antigen's existence. So now this says that I am O blood type and I'm large in size. This means I'm A blood type and I'm large. This means I'm O blood type and I'm small. And this means I'm A blood type and I'm small. So you can interpret it exactly like that. So it will be a binary relation if we forget about B blood type. Okay. So for now, I'm going to just focus on the other interpretation, because it's exactly the same binary order. I will focus on just the blood types instead of this, but it is equivalent. This interpretation is equivalent if you had two types. Okay. Yes. And since I talked about this, I'm not going to talk further about it unless there's a question. So size compatibility in this toy model can be reduced to, if it's only binary, if you get rid of B antigen's existence or non-existence, if you don't consider that kind of compatibility, will be this kind of binary vector compatibility, two-dimensional binary partial order. We will define this partial order to denote compatibility. Yeah. All right. Okay, so now, here's the problem. So like I said, I will just call them blood types. So I will use this interpretation. So these blood types, I will call them compatibility types, because now they are equivalent, because there's no size compatibility. And each patient and donor triples are denoted by their blood types. So the first letter is always the patient. Okay. The second and third are the donors. So these are the donors that patient brings. These are the blood types. So XYZ is equal to XZY. Okay, just we could have probably used a comma here instead of a dash, but that's what it means. All right. And a lung exchange problem consists of we are going to look at the number of patients from each type. Okay. But which types will be in the exchange? Which don't have any incompatible or at least one incompatible donor. So if there is a type X, Y, Z such that Y can donate to X and Z can donate to X, the number of such patients will be 0 because they will never come to exchange. They will directly receive from their own donors. Okay? So the first question is, let's just look at two-way exchanges in which you match one triple with another triple. That's it. Okay? So which types can ever participate in exchange in that case? So only there are two types. Or two, it's not exactly two types, but we will have A patients and B patient types can participate in exchange. That's the result. And what can they look like? They can look like A, Y, B, and Y can be any of these, O, A, B. Or B patient, Y can be anything, O, A, B. And AB patients never participate, because AB patients are always compatible with their donors. And AB, if you're an AB donor, it turns out there's no way you can create an exchange because you need an AB patient if you're an AB donor. But AB patients never participate in exchange because they can receive from their own donors. So if you're an AB donor, you are unlucky. You cannot create an exchange possibility. Okay? And for two-way exchanges, if you want to only match, because this is the easiest one to conduct, even this requires 6 operations. Right? A two-way exchange requires 6 operations in any condition. So even in this case, you would be able to match only A patients and B patients. Okay? So in this exact model, in the kidney exchange, we have the result would be you would match A patient B donors and B patient A donors. Only two-way would help these guys. So that's the equivalent thing if you have one donor, okay, if you want to think. But kidney exchange is more elaborate. There will be A patient and O donors coming in because they will have tissue type incompatibility between them. And this will be more elaborate because they will have size incompatibility in between them, which are kind of different. But so these guys can also come. So, but I'm here right now shying away from size compatibility. Okay, so that reduces to this simple model in the kidney exchange. All right, so and who can exchange with whom? So if you look at that, A or B can exchange with, because of this O donor can be used as a joker. It can, he can give it to A or he can give to B, okay? So in a way, A or B, and this, remember, you need 2 donors of the same blood type or a better blood type to get a two-way exchange. So you can create a two-way exchange with these two. How? This O gives to A, this A gives to A, this B gives to B, this B gives to B, and you can create. And it's very simple. You can, actually, by addition and subtraction, you can look at number of donors, number of patient blood types different, and you can say whether a group of people create a feasible exchange or not. So it's just a simple supply-demand equation. You can just find that, okay? And then you can create surpluses out of that, which donors are more valuable. For example, here, O blood type donor is never fully utilized because there's no O blood type patient. And he cannot participate in a two-way exchange. But it turns out you can match these guys with these guys with these guys, etc. So this is the compatibility graph, mutual compatibility graph. So this is how it works. So, so these guys have the highest opportunity to be matched. So you can easily see it's a two-sided matching problem. We create a two-sided matching problem. It's actually very easy to solve. You can just use off-the-shelf algorithms. We know they're efficient. You can just solve what's the maximum number of people that can be matched, etc. But it's good to know this graph is simple enough. We can come up with an easy algorithm actually to solve this. And the algorithm is quite easy. Let me show you. This is the algorithm. So you first clear as many as these edges down here. Okay. So then either this is excess or this is excess, but not both, because otherwise you could have matched them with each other. The same here. Okay. Now, what you are going to do is then you are going to look either this one will be excess or this one will be excess. Maybe if they are exactly demanded with each other, they will just clear each other. Or this one will be excess, or this one, this one will be excess. Now you take these middle guys into play. Instead of using AOB's own BOAs with each other, you try to go to the edges. So either this edge will be relevant or this edge will be relevant. Similarly, either this edge will be relevant or this edge will be relevant. But you will try to maximize the number of matches using these two edges. And whatever is remaining, they will only be matched either from here or here, and you are going to match those two with each other. So that's simple enough. It turns out this idea actually this idea is very powerful, not only for two-way exchange. When we talk about three-way exchange, unlimited size of exchanges, this kind of an algorithm, this kind of sequential clearing algorithm, of course you have to take things into consideration, can actually be utilized to clear and define the maximum number of transplants. And if you don't want to use it as an algorithm, just this tells you what is the maximum number of people that can be saved. You can write it as a closed form, easy expression. And this is this expression, so it may not look very easy. But this is the number of patients that will be matched will be 2 times the minimum of these 4 numbers. So those 4 numbers are, so N1 is the number of A patients to the left, and 4 is the number of B patients, okay? So in a way, I'm comparing, this is which side is long, B side or the A side. This is what I'm doing. So if I had an edge from here to here as well, this would be sufficient. Just I will compare this, then I can create a complete matching. It's easy to, it's almost obvious to create. But I don't have an edge from here to here or here to here. So I need to do more, be careful. If there's no edge from here, this is not just, I don't look at the minimum of these 2 numbers. I have to also look at the minimum of this sum plus this sum and this sum plus this sum. So that will take care of the, since we don't have this, you need to go through these guys to go there. So that takes care of that. So the minimum of these 4 numbers, since every exchange has 2 patients times 2, is the number of patients you can save. So you can do this 3-way, a bit more elaborate. You can do it for, so I'm not going to talk about that. I want to talk about liver exchange. But I want to show you this participation lemma. So let's say, so this is now, we are already in the like theoretical boundary, in the sense that we know that most likely this kind of exchanges will not happen. Why? Because it requires huge coordination problem if you go beyond 2. But nevertheless, we want to claim that we want to do it because there are huge gains if going from 2 to 3. That's the reason we'll look at that. And if you have no size constraints on the exchange size, then actually now you can also save all patients. Okay? But in the kidney exchange, this is all you can do still. You cannot do more than 2-way. More than 2-way you cannot help. If you didn't have this size compatibility requirement or tissue type compatibility requirement. So now I can now start to save all patients in exchanges. How does that work? Well, it turns out that if many of these O patients will also have an O donor. Okay? Even if it doesn't have an O donor, it can have a B donor. This B donor could be valuable to save the short side of B patients. Or it could be maybe A patients are on the short, so it could be feasible to save them. Okay? And how can I help them? I can help them through these middle guys, BO. So if I put 2 of them together, they will create 2 O donors. So I can save an O patient. So by putting this together, or these together, I can save 2 O patients. So that's the idea. You can increase the number of transplants by putting which people who couldn't be saved in the simple kidney exchange without tissue type incompatibility, here you can save them. So that's the nice thing about this. And again, AB is hopeless. AB patient already saves himself, but AB donor, if you're an AB donor, you cannot use it. And if you're an AB donor, you will never participate in exchange. So that's out there. Okay. So what we will do is in the rest of this paper, I will assume since there are many of these patients, in the long run, you will see lots of O patients and incompatible donors. In particular, this type, O patient, O donor, and A donor, or O patient, O donor, and B donor. There are many of them. Suppose you can always basically squeeze them one in to an exchange to to save them. Okay, so I'm not going to talk any of these, but I will give you this result. This is two-way, three-way. First of all, the first, in terms of what is the largest exchange size you need to save the maximum number of people? In this simple model, you need largest six-way. Okay, so any larger exchange or any exchange which has larger exchanges, more than 6 triples, can be decomposed, can be cut, etc. Or you can sometimes have to substitute one triple with a triple that you were not using before. But you will always maximize the number of people matched with using exchanges which are at most 6-way. Do I have to use 6-way? Can I do it with 5-way? No. Also necessity. So you would lose. There could be a weird problem like this in which you won't be able to reduce that. And it is exactly supply and demand condition. But let me show you for simplicity. So you see these are these middle guys. A patient, O donor, B. So this O can be used in either way. But in this problem, I will use them to save O donors. O patients. B patient, OA, B patient, OA. So there are two of these. Okay, and I have 3 O patient, O donor, B donors. Okay, so I mean clearly this O's gonna donate to their own patients, and I have to use these O's here. Okay, and then just sum up them the number of B's. 1, 2, 3, 4 B's here, 2 B's here. So it's 4 donors are needed for 2 B patients. Good. 2 here, 1 here. So good. So this is either you can conduct this in one exchange or multiple exchanges, but this market will clear for sure. Supply equals demand. But can you cut it to smaller exchanges? The answer is no, because to match these 3 O's, you need these 3 O's in the same exchange. Okay? If you take this one of them by self, let's say, can I take one of these by itself? Then I will have 2 of these. I'm sorry, you will have 1 of these in this exchange. Okay? So what can I do is that I'm going to, for example, I won't be able to match this guy by himself without decreasing the number by using less number of people. Because whenever I include more than 1 of these guys in an exchange with this, then I won't be able to do this too. Okay? So that's the idea. And you cannot do that if you look at that. Right? Because this has a B patient. So this B requires 2, for example, A. But to get 2 A's, you need one of this one. So once you put these 3 together, you cannot match these 2 at the same time. So you cannot cut it less than 6. And the idea is, again, this O, whenever you have an O donor, you can save 1 additional guy, in addition with the help of others, basically. So you can double this. So these guys would make a 3-way exchange, but by squeezing these guys together, you can save 6, and you cannot make it smaller. So then we can find the maximum number of, using this idea, you can find the maximum number of people. It's kind of a demand supply, but there's an integer problem, so I can find it to up to one approximation of the maximum number for a given problem by looking at it just. And what I do is, so this number is given by this M number plus these numbers. Okay, just forget about this. That's just 0 or 1. So M number is just A patients I can match plus B patients I can match. And this is O patients I can match. These are the ones that I can squeeze in using AOB. And these are the ones that I can squeeze in. These are the B patients I can match using BOA. So if you look at how many A patients I can match, well, it cannot be more than the number of A patients. It cannot be more than the number of A and O donors, because O can give it. So I divide it by 2 because 2 donors save 1 patient. And this one, this number SP is basically, this is the, given the B population, because we have the other side B patients, how many A's I can save. This is what it gives, okay? So minimum of these 3 numbers give that. So these numbers also enter here, but actually these numbers also, you don't have a boundary of the A patients because, O patients, you don't have to put it here because this number I assumed there are as many as possible O patients. That's the long run assumption, so I don't have to put PO here or PO there. So that's the idea. So you need to check these three things. Okay. So without further ado, let me show you some exchange simulations using the US data for the disease donation. With who enters disease donation, we looked at their characteristics. We used like American people's age distribution, size distribution based on those ages, gender distribution, etc. So I would like you to just direct you to just this one, okay? Just this last line. First, we assume there is no size constraint. So this is the exercise I've done basically by those numbers, computing numbers. But now I also assume there is a size constraint. And size constraint is that you can only receive donors as large as you, okay? And I assume it is random matching. So donors are randomly matched. Of course, in reality, a large person can be married to a larger person or also large person. But I'm going to just shy away from that. So these, if you wish, these are actually kind of big numbers. So probably the real gains are going to be smaller. But to show you how much they can get, I think this is a nice simulation. So if you have only 50 pairs, okay, when you put them together, about 8 of them, so in the last line, because of the size constraint, can get direct donation. The rest, 42, will go to exchange. You only look at 2 ways, you will get about 5 more patients on average to be matched. But if you look at 2 and 3 way, this number is already doubled. Okay? Out of that 42, if you look at 2, 3, and 4 way, this number goes to 10.2. Okay? If you look at 2, 3, 4, and 5 way, this number goes to 12. If you look at unrestricted, these numbers go to 15 or 15.5, like triple of this number. Okay, totally, this and this plus. So in a way, there are really gains from conducting large exchanges, which didn't exist for kidney exchange. In kidney exchange, usually, this would saturate after 3-way. And that was the reason 3-way was recommended, but not 4-way. And people don't look at 4-way much right now. But for lung exchange, clearly larger sizes are going to get, and this is a big hurdle in the sense that you need this kind of coordination. Okay, so this is my computational power. I can only simulate up to 5-way, so I need to rent Amazon servers, but I'm not going to do that. All right. How many minutes do I have? 5? 6?
No, actually 8, 9.
Okay. So let me give you the punchline of this liver exchange model. So what I'm going to do in the liver exchange model is that now instead of 2 donors, I will go back to just having 1 donor. Okay? But now I'm going to put this size compatibility requirement as a 3rd dimension. So I will have the blood types being represented as whether there is an A antigen or B antigen, plus whether you are large or you are small. Okay? So now we have this kind of a compatibility relation. Instead of 2-dimension, I'm on the 3-dimension. Okay? So the dominant type, the 111 type is OL. You are both O blood type and you're large. And the bottom at the lattice, if you are AB and you are small as a donor, that's the worst. I mean, this is for the donors. Okay? And you have this kind of relationship. So equivalently, since I can replace blood types with 2 numbers and size with, again, 1 number, so it becomes a 3-dimensional binary vector, and I can use just greater than or equal to standard partial order to determine compatibility. Okay? So now in the liver exchange, you only need 1 donor, right? So each patient and his donor can be represented by 1 vector and another vector of this sort. Okay? So we have 2 vectors together. So the first vector will be patient's characteristic. The second vector will be donor's characteristic. If the donor characteristics are greater than or equal to the patient's characteristic, then this patient will not come to exchange because the donor can donate to that. But if they are not comparable, they will come to exchange. Okay, and who can we save in this case? Can we do we have similar problem with ABs, etc.? Okay, so I'm gonna just skip that. So this is the picture. In a two-way liver exchange, we have we call this some kind of science fiction spaceship shape. So we have, look at that. So we will have at these corners people who could almost donate or receive from their donors, but they have only zero, they were mismatched at only one of these 3 digits, basically. So these are actually quite valuable. You can see they could almost receive. That means the donors are quite valuable. They have at least 2 ones, okay? So I can utilize these outer corners very well. So if I have this kind of line, this means this pair and this pair can exchange. That's what it means, okay? The unluckiest ones are just the opposite kinds. Actually, there are certain ones they will never receive, and these are the AB patient equivalents. ABS, for example, will never be here. If there's an ABS donor, you cannot match that donor because all patients of ABS or 000 type of patients will go to direct donation, and you will have a picture of this sort. And we will use again. So I'm totally going to skip this algorithm, but there's a nice piece. So you can use a greedy kind of algorithm, but not too greedy. You have to choose which edges to choose. You can clear and obtain the maximum number of transplants. So you first begin with this, and then you look at insights, and finally you look at these edges to clear. Okay. So this will give you the maximum number of two-way exchanges. So this is the only thing we looked at this point. So this is in progress, like I said. But I will show you. So this is more the graph theory part of it. But let's look at more the economic question. So what is the benefit of this exchange? So here is a simple model with and without size constraints. So I will think about there is a medical breakthrough. Suddenly you don't need size constraints. Or the doctors are taking extreme risks. You don't need size constraints. Okay? So that will be my baseline model. So baseline model will consist also lambda 1 is number or measure of the people of a certain type. So these are X patient, Y donors. These are just the blood types. Okay? Because size is not important. So this is my baseline population is patients with X patient, Y donors, and size doesn't matter because you can directly receive transplantation. Okay. Now, but next, suppose there are at least 2. So in my model there were 2, but there could be more. Actually, that's more realistic. Suppose there are sizes of people, which is a total order. L is the biggest person. 1 is the, let's say, smallest person in terms of size. And these patient and donors are IID again, just are given. With probability P1, you become size 1. Or with probability PL, you are of size L. Okay? So now in this population, in this second model will be the patients with their blood types and their sizes. S and S prime are their sizes. Okay? And the way it just corresponds to the first model is that, so I will use lambda 2 to denote the measure here, and lambda 1 to denote the measure in the first baseline model. So the lambda 2 measures are just lambda 1 measures times the probability of this being size S and probability of this donor being S prime. That's it. Simple enough. And on top of that, compatibility requirement in the baseline model, you just need blood type compatibility. In the induced model, in the size compatibility requirement model, you need both blood type compatibility and size compatibility. Okay? So I'm going to make this again long-run assumption. We will assume that if there are many patients of this type, like there are many O blood type patients, for example. Okay? So all patients, A blood types are greater than A blood type, O patients. Actually, this number will be 0. Okay? So that's just that assumption. All right? But that's the only assumption we will need. So I'm going to classify pairs without the size constraint into 4 groups. Okay? We call this type 1 or self-demanded. So these are O patient, O donors, A patient, A donors. Okay? The same blood type with your donor and patient. This is, we call them over-demanded types. Okay? So this is A patients, O donors, B patients, O donors. So these have more valuable donor than them. And without the size constraint, none of them will come to the exchange because they will directly receive. But with size constraints, some of them will have, these will have a large patient, a smaller donor, so they will have to come to exchange. And type 3 is just the opposite, under-demanded. O patient, A donor, just the opposite of these guys. So they will be always there. And this assumption just says that these guys, there are many, many of these guys. It's a big pool, and they're waiting there just to be matched. There are excess of them. And finally, this fourth type is just A, B, B, A. A patient, B donor, that's the middle line of the partial order. So neither B is compatible with A or A is compatible with B, okay? And P star will be that odds that a random patient donor being themselves with each other size compatible. So what is this? This is the probability of I'm type L. So we use K as the maximum number here, okay? And my donor being at least L or higher. Just a very simple number, okay? So let's look at the total number of transplants in both cases. So suppose we have 2 technologies, direct transplant and two-way exchange, okay? So direct transplant, when there is no size compatibility requirement, all of these guys will immediately receive their own donors. And all of these guys will immediately receive from all donors. So all of this measure of type 1 and type 2 will go out immediately without coming to the exchange. Okay? So who is left? Only AB. This is what I was telling you. This is exactly like kidney exchange without this type. So only we can match A and B. And the minimum of these numbers will be the short side. We can match twice the minimum of these two. This comes from two-way exchange. What about with the P, with this size compatibility? Now, the direct donations will decrease, right? So only P star times of these guys will get. So these are the ones who are compatible, and P star times of these guys. But now, the remainder of, okay, type 1 is useless for exchange, but type 2 is very useful for exchange. So the remainder, 1 minus P of type 2 will come to exchange, and it's going to save twice its number because there's an excess of OAs, OBs, etc. So I have this additional term here. Well, this term will not change because for any AB which is type small a, there's a large, for a SS prime AB, there is a corresponding SS prime BA. So we'll be able to match all of them again. So this is the additional term, but this number is decreased by type 1. So in the end, it boils down to this. Without size constraints, you can match more people if and only if number of type 1s are more than number of type 2s. And if you put, so this is like for two-way. For three-way, this number will be actually, you require more numbers here. So this will get, okay. So with the size constraint, you can match potentially more depending on how much of these guys come to the depending on. And it's safer because you will give larger examples. So I'm not going to show you the numbers, but that's basically it. That's the end of my presentation. Thanks for your patience. I will talk about, right now we are working about the incentive problems in liver exchange, the kinds like how do you prevent somebody pausing to give his right lobe if he really wants to give his left lobe, those kind of things. Okay, and right now also there is some, we were in Japan recently, my co-author Tayfun Sönmez, myself, so I had an ex-student who is a professor in Japan now. We were discussing about implementation in Japan. So there were some transplant surgeons we met. Well, there's lots of bureaucratic problems. But I'm used to this kind of things because I talk to real practitioners. It takes forever this kind of being done. So we'll see. Especially lung exchange, they were very excited about lung exchange. Liver exchange, it didn't create as much, for some reason, enthusiasm. So we'll see whether it's going to catch up. So this week, actually, Morimitsu Kurino, who is my ex-student in Japan, is visiting Okayama University, the #1 lung transplant hospital in the world. So we'll see what's going to happen.
Thanks. We can take a couple of questions, I guess.
Just don't drink too much, your liver.
Is there some possibility for international trade? Like you can imagine like one big city with very large people donate to some Asian country who in exchange build them perfect public system.
So that would be actually very nice. I mean, you would think that these kinds of things could be done very easily, but the problem is, in the end, there are lots of the health system who pays this real operations, etc. All of these things, incompatibilities in the insurance systems, they affect. So it's kind of difficult. And it should, I totally agree with you, but we would be lucky if this Okayama University begins it, but then other places join in. So in the US, that's exactly what happens. Just one state, we helped one state to start, and the others joined in. So maybe. Yes.
So in the setup here, if I'm say an AB and I've got a couple of O donors, I never get into the exchange.
Yes.
But I'm really valuable to the exchange because I've got some great donors who
Exactly.
are highly valuable. I mean, has anyone looked at whether, particularly in a public system where the government's paying for the transplant operations, if they can, how much better benefit you get if you say, well, sure, you can come along and you could do it with your donors, but it's a public system, you have to participate in the exchange and swap around.
It's actually, I think that's the most important question in this, because these, maybe not in lung exchange, but in kidney exchange, otherwise we are just pushing the boundaries using this operations research techniques, this and that, but this is gonna, okay. So my research in the last 2-3 years on kidney exchange, the part that is explicitly on this issue, we looked at different ways to incentivize people without using money. What can be the tools? What are the acceptable systems? Like one idea is the following, because this is done already for donors. So if you're a live donor, regardless of who you donate, if your organ fails in the future, you get a priority in the deceased donor list. You don't have to participate in exchange, no matter what happens. That's very common in all over the world. You get a very high number, like a big number of points, and you are almost, certainly will be matched very soon. So can we do this for these pairs or these like triples? Let's say I come to the system, I bring these valuable donors. In return, I get a guarantee. If something goes bad, I will get a priority in the deceased donation list. Okay? For kidneys, that can be done. But for this lung or liver, well, there isn't much deceased donation anyway in the countries where it would happen. But for kidneys, exactly. So that's the idea. So that's something we are trying to push. So we have another paper. We exactly analyze both in a dynamic model, but it's a continuum model. Entries with exits, what happens, how it affects, and then we look at, so it's not really empirical, but we look at some, calibrations of what are the results, how many people would you save, how many people, how many years people would wait less, those kind of things. But that's the most important question at this point for kidney exchange. Yeah, thank you.
Okay, well, please join me.
Well, thank you very much.